And first of all, I have to say that I have to correct the very last thing I said yesterday, okay? Because I made an error. Okay, so let me share the whiteboard. Okay, yesterday we saw that in the CCM buck boost, the current through the inductor is the classical one. So it is the red curve you can see in this this whiteboard. Okay, and then you have a maximum current, a minimum current, and a current ripple. The average value is called IL. So the average value is given by this sorry. Okay, this one. Okay, this is IL, average value, and this is the expression of the current, peak value of the current Imax. Okay. Now move to the diode current. Okay, the diode current is the same of the inductor current when the switch is off, and so the current is given by this waveform here. I don't know why I cannot have my whiteboard completely. Okay, good. Okay, here. Okay, this is the ID current. Now the ID current is just as a pulsed current, which is the same of the inductor current during the off. Okay, during the off. It has the same peak current of an inductor current, Imax, the same Imin is here. The average value of this diode current is the same of the output current. Okay, the red curve is the average value. Okay, the average value is the output current, I naught, because no steady state situation, no DC current can flow through the output capacitor C naught. And so as a consequence, the average value is given by this expression. Okay, is negative I naught, which is negative V naught over R. What about the root mean square value of this current? This is not, say, something that we directly use for the computation of conduction loss in diode, but is useful to derive the root mean square value of the C naught current, okay, C naught capacitor. So we have to derive it, and you can derive this root mean square current by apply some approximation. One of the most employed is the flat top approximation. So you can approximate the curve by the mid value between Imax and I minimum. So it is exactly average value of IL. So you have now a rectangular waveform of the current, and then you can get this expression, okay, in which IL average value is given by we derived before, and so it is V naught over R divided 1 minus D minus 1. And so if you replace IL average value with that value, you can find the root mean square value. So this is the correct value, which is also in the slide. Okay, yesterday I put a D at the numerator, but this is not correct. Okay, so continue discussing this CCM waveform of the current, for example, taking into account what about is the switch current. The switch current is the current that flows through the inductor when the switch is closed. So we can draw this switch current, I switch, in this way. TS, T on, the same peak value, I max of the inductor current. Here you have I minimum current. The mean value between I max and I minimum is the average value of the inductor current IL. And then also you have an average value, this one, of the switch current, I switch. Okay, the average value of the switch current is the input current, okay, because you have the switch connected exactly at the input side. So this happens, for example, in the back. Here you have the DC input current. No current can flow, no DC current can flow through the C-in capacitor. And then you have here the current I switch. Okay, so the average value I switch is the same of the input current. Remember that in lossless converter we have that the input at the output port, so the P0 input, is the same of the power at the input side. So you can have P0, I0, which is V in I. So in that case, the input current is simply the conversion ratio multiply the output current. So this is I0 MCCM. I0 is V0 over R. We can also take the absolute value, because remember that V0 is negative in buck boost, and then you have D1 minus D. Okay. The root mean square value of this current that can be useful to compute the conduction losses of the transistor in case you have a MOSFET, for example, and it is also useful to derive the root mean square value of the input current, so the current through C-in. Again, you can find the root mean square value by considering the approximation of the flap top. You can flat the top of this, say, trapezoidal current by taking the value, the IL, so the average value of the inductor current. So again, you can have something which is IL average value square root of D. So is V0 over R1 minus D multiply the square root of D. Okay. There is another important parameter that you have to consider when you, say, design a converter, and that is the voltage with which that the switch can support and can withstand when it is off, when it is open. Okay, in that situation, the maximum voltage is when the switch is open. What happens is that the current flow, remember the circuit here, okay, when the switch is open, the diode is on. When the diode is on, the voltage across the inductor is V0, and so the switch has a voltage on it which is V in minus V0. And so this is the maximum voltage that you can have in across the open switch. V in minus V0. Remember that V0 is negative, so across this switch you could have a very large voltage drop. So you have to buy a transistor which breakdown voltage could be, in this case, very large, because it's a summation of the input and the output voltage. So let me move to the input current, for example, the input current, the current through the input capacitor. Okay, see here. This current here can be derived by looking again to the node A, to the node, sorry, in. We call this node like in. Okay, we have C in, which is here. So let's suppose that the direction of the current is this one. Here we have the input current, which is just a DC current. And then we have the switch current. Okay? So at the node in, you have the Kirchhoff current law, which is I switch is the same of I in plus IC in. What is of interest now? Of interest the root mean square value of this current. Okay, and if you want to get the root mean square value of this current, you can apply the quadratic Kirchhoff current law. In this case, you have that the current I switch has both AC and DC contribution. The current at the input is just a DC current, and the current C in is just an AC current. So if you want to find out the root mean square value of the input current or the C in current, you can have the difference between the root mean square value of the total AC plus DC current minus the DC contribution. We know this root mean square value of the switch, which is V naught over R1 minus D square root of D and then we also know that E in is the switch current average value, and so we can say that E in square value is V naught over R D 1 minus D square. Okay, this average value was computed before. So if you say take this difference, and this difference leads to V naught square D r square 1 minus d. Okay, so the root mean square value of the input capacitor current is exactly the root square of this quantity. So is V naught over R d 1 minus d. And since V naught is negative, you have to take that. Okay, which is the waveform of this current flow into the input capacitor. Is simply the current through the switch less its average value, less the average value, which is the input current. So if you want to have a plot of this current, is something like something like this. Yes, T on, etc., etc. Okay. Another important parameter for capacitor is the working voltage, which is the maximum voltage across the capacitor. And in that case, the input capacitor has a voltage VC in maximum, which is the maximum input voltage V in. Maximum. Okay. Move to the output capacitor. Okay. C naught. Now we have here a diode. The node is called out. Suppose that the direction of the current through C naught is this one. Then you have here I naught, which is a DC current. And here you have ID, diode current. Again, you have the Kirchhoff current law, so we have that ID of T is negative I naught minus I C naught. Okay, and if you want to find out which is the root mean square value of the output capacitor, you can apply to this law the Kirchhoff, the quadratic Kirchhoff current law, because the current ID is a current that has both the AC and DC component. I naught is just a DC current. IC naught is just an AC current. Okay, so quadratic Kirchhoff current law is IC naught root mean square current, which is the difference between the ID current, root mean square value, and I naught. Okay, now we have all the component of this equation. Okay, because the ID root mean square value is already computed. So ID, it was V naught over R 1 minus D. while I naught is simply V naught over R. Okay, if you take these two, you square them and put in the previous expression, then you can find that IC naught root mean square value is V naught over R d 1 minus d. Okay, and this value is the same value you can get for the input capacitor. Okay, remember this happens because now in the buck boost, both the input and output capacitor have a large electrical stress due to the fact that they have a MOSFET in the input side and a diode in the output side. So no smooth current, like for example in the input port of the boost or output port of the buck you can have now. Both C in and C out are stressed, so they have a large root mean square value that you have to manage by choosing specific capacitor. Okay, so this is what happens in CCM. As you seen, this kind of computation are basically always the same. Okay, there is no differences. Okay, you have maybe different waveform, but typically the diode and the MOSFET current are always the same. So you can have, say, more or less the same kind of computation, and you can take this, say, derivation, just an example of computation you can do in your examination or when you design your converter. Okay. Let me charge the slides. Okay. Oh, of course, what I said is already written here. Here you have the standard diagram with all the current and voltage waveform that are typical for, say, PWM converter. And what I like to talk here is the DCM. As I said at the beginning of this discussion, DCM is the standard operating mode for the buck boost. And this is also typical for the boost. Okay, this will be clear in next lecture when we talked about closed loop control. Okay? But this is basically is due to the fact that in CCM both the boost and the buck boost are very difficult to stabilize. Okay, it's very difficult to make possible to have a constant output voltage against the variation of the input voltage, the output current, etc., etc. Okay, so it's easier to operate them in DCM. Okay, of course, in that situation, you could have a very large electrical stress of components, so you cannot apply the boost and the buck boost for very high power level at the output side. Okay, so the nominal power, the rating power is not so huge when you have to operate your boost or buck boost in DCM, due to the fact that in that situation you could have a very large stresses, and so large component, expensive component, they are heavy, etc., etc. So typically they are employed in DCM, but in the lower range of output nominal power. So what happens in the DCM? Okay, I increase the output load, and when I increase the output load, the current reduces. Specifically, what happens that the ripple remains the same because there is no connection between the ripple and the output resistance, but it's the average value of the inductor current that reduces. Okay, the same reasoning that we have already for the other configurations. At a certain point, the minimum current through the inductor would go, say, negative, but when this current is zero, at that situation, the diode cannot support a current flowing in the from the cathode to the anode, so the diode remains interdicted, remains off. So there is a T1 period, which you have the switch which is on and the diode that's off, as happens in CCM. Another period T2, in which you have the switch off and the diode on. And then we have a third time interval, which is called T idle or T3, in which both the switch and the diode are off. In that situation, what happens? Let me again share the whiteboard in order to derive the conversion ratio in DCM. So, buck boost DCM remember that the circuit for CCM and DCM is always the same. Okay, there is no topology changes when you want to go in DCM. Just the values of the components are changing. Okay, in that situation, what happens to the voltage across the inductance? Okay, VL. As I said before, there are two intervals that are exactly the same interval you can have in CCM. And so you can have the T1 period in which the switch is closed, the diode is off, the voltage VL is exactly like V in. Then you have, by the way, we can continue to define the duty cycle as the ratio between T1 and TS, which is the switching period. Okay. So we have T2, and in this time interval T2, you get the switch open and the diode on. So VL is V0, and V0, remember that it is negative. This happens during T2. And then you have a third time interval in which both the switch and the diode are off, and so the voltage across the inductor is null. And then the cycle repeats itself. This is T3. Again, the fact that you can have here a zero voltage level is something that depends on the fact that the switches are both open. Okay, but in practice, due to parasitic capacitance that you can have across each real component, like for example here across the diode and also across the capacitance due to the terminals, for example, then what happens in this region is that you can have some, say, ringing, some oscillation in the voltages. Okay, this was observed in the lab, for example, for people working on the buck, but it always happens due to the fact that in that specific situation you have a resonator. Okay, and so you have to dump out this oscillation by using some specific circuits. By the way, Friday afternoon there is the lab. Okay, this is confirmed, and so students that are interested, if they want, they can book on the portal, student portal website, their seat in the LED 5. Okay, for continuing the back experience. Okay, I don't know what happens next week, but we proceed, say, week by week, and so if you are interested, you can book and go to the lab Friday afternoon at 2:30. Okay. What happens to the current? If you have current through the inductor, we are in DCM, so we have to accept that the current goes to 0 for a short interval during TS. So in this first part, T1, the voltage is positive across the inductors, is constant, so we can say that current increases. Okay, up to a point that is the peak point, peak value, Imax. Then you have a negative slope during T2, since V0 is negative. Okay, and then the current that flow during T3 is 0. Okay, so we have a slope which is V in over L. The slope here is V0 over L, standard derivation, okay, of the slope. The goal here is to derive M dCm, which is the V0 over V in. We know that this parameter should be negative because V0 is negative in buck boost, but we have to derive it. Okay, it's not the same as the MCCM we derived in continuous conduction mode. Let me derive this parameter by adopting, say, some energy consideration. Okay, the first consideration that we can have is what happened during T1. Okay, T1, switch is closed, diode is off. We are in what I call at the beginning of my discussion the charging phase. Okay, the input voltage V in is directly connected to the inductor, which is in parallel in this phase to V in, and the inductor is energized. Better, the magnetic field gets energy from the input port. Okay, so what does it mean? That the inductor gets energy from the input, and thanks to this energy that draw from the voltage V in, its current can, say, rise up from 0 up to Imax current. Okay, so we can say, okay, that the energy that is provided to the inductor during T1, during the charging phase, is responsible for increasing the current up to Imax. So we can say that we can have this kind of expression. Okay, the energy which is stored in an inductor is 1/2 the value of an inductance multiplied the peak current that can have at the end of the time interval T1. Okay, so in the charging phase, you have this energy. Remember that Imax can be easily derived, okay, because Imax is what? If you look at the current of the current waveform through the inductor, okay, Imax is the peak value. Okay, we know the slope. We know that the time interval is T1, so simply multiply the slope by the time interval T1 and you can get the peak current Imax. Okay, so it's very slow this morning to change, to write. Okay, V in over L, which is the slope, multiply T1, and this gives the peak value. Remember that T1 is given by the duty cycle multiplied Ts. So we can get V in over L duty cycle and then divided Fs if you want to speak in terms of frequency. So using Imax here, okay, in place of the Imax here, I have that the energy stored in the charging phase in the inductance is 1F L and then Imax square. Is L d Fs square value. So is V in square V square 2L, because we have a L here and then you have L square here, Fs square value. Okay. This is the energy that we have at the end of the charging phase, so when the time t is equal to t1. So this energy is transferred to the output side of the buck boost during the time interval t2. During the time interval t2, what happens? The switch opens, the diode on, and so remember, then we have connection between the inductance L that stores this energy and the output side. So there is an energy transfer between the energy stored during T1 across the inductor and, say, the load during the discharging phase or during the time interval T2. So this is the same energy that we should provide, that you provide at the output side in the second time interval T2. Now look exactly at the current through the inductor, okay? During T2, as you can see here, the current through the inductor from Imax goes down to 0. So the inductor discharges completely during the time interval T2, okay? This is not the same that happens in CCM. In CCM, at the end of the time interval T2, so at the end of the cycle, the current through the inductor is not null, because the current is always positive. But in this case, we can exploit this fact in order to derive the conversion ratio. So during time interval T1, which is the charging phase, we computed the total energy which is stored across the inductance. And then during the time interval T2, this energy is totally provided to the output side of the inductor, discharges completely. And so we can say that its energy, EL, is also the energy that we provide to the output, okay? So this energy is the energy that make possible to, say, define the output power. Remember that the output power is V naught square over R. This output power is totally due to the energy that is stored into the inductor and that is stored during the charging phase T1. So let me derive to move from this energy computation to the input power, okay? The input power is simply the energy multiplied, is the energy EL divided the period Ts, okay? So it is EL multiplied Fs, and so you can put this expression here, you can simplify it Fs, so the input power is V in square, D square, I have to go very slowly because I don't know, but it's difficult to write. 2L Fs. Okay, so this is the input power, and this is the output power. The two are the same, so the input power computed as the energy provided to the inductor should be the same of the output power because the inductor is completely discharged. So we can say that P naught is equal to P in. And then let me change the page. Okay. Then we can have V naught square over R, which is equal to V square D square over 2L Fs. Okay, P in, which is equal to P naught. So we can have V naught over V in square is equal to R D square over 2L Fs. Okay, so from this expression we can derive M D Cm, which is equal to V naught over P in. So it is D R 2LFS. It's not finished here because M is negative, as I said before, so we have to take into account when you have this the square root of this expression, the sign which is the negative. Okay, so this is the conversion ratio that you can have in DCM. Okay, some comments about this expression. It depends on D, and this is useful for control because D is the control information. Okay, is the way from the external I can change the output voltage. Okay, so D is the control input if you want, and so this is useful. I can control it, okay, by control signals. But also depends on R, depends on L, and depends on Fs, like all the conversion ratio in DCM for all the converters. If you look here, it depends on R in the sense that if R is increasing, also V naught is increasing. Okay, if, for example, R goes to infinite, what does it mean? That I'm disconnecting the load, so I'm, say, extract the load R from my circuits, then V naught becomes infinite. And so that means that my output diverges up to the point that the output electrolytic capacitors overcomes its maximum working voltage, and so typically it explodes, okay, like popcorn, and then you cannot use it anymore. So pay attention. This also happened for the boost, okay, but this is not surprising because the output side of this converter is exactly that of the boost, okay? The diode has opposite polarity in the boost, but okay, it has also a diode, always a diode in that position. So What happens here that in the boost, in the buck boost, pay attention not to disconnect the load if you want to save your converter. Okay, so this is very important. Specifically in the lab, when you will work on the buck boost or the boost, when you want to measure the output resistance for your measurement planning, and you disconnect the load just to put the load across a multimeter, okay, to measure its resistance, typically this leads to malfunction of the buck boost. Okay, so please don't do it. Okay, so parameters of the DCM buck boost converter. The classical parameters are the audio acceptability, the small signal output resistance, and the gain. Okay, audio acceptability. Is defined as small variation of the output voltage against small variation of the input voltage. This is always M, in this case, the conversion ratio for DCM. And so this is minus D, etc. Square root of R to LFS. Okay, small signal output resistance. This is delta V naught over delta I naught. Remember that in CCM, for all the converter topology, this is null. Okay, that means that you have a very good power supply, so a very good voltage source. Okay, but here in DCM, this is not null. It's different from zero. Specifically, V naught is given by this expression here. So let me express V naught using the conversion ratio. R I can express as V naught over I naught. Okay. Take the square of both sides. V naught over I naught to L Fs. Okay. Simplify V naught here with this one, so you can have V naught, which is V in square G square 1 over 2L, then you can have I naught Fs. Okay, now you can apply the definition. Okay, you can have the delta V naught versus I naught. This is basically you have some constants, V in square, D square, you have also 2L Fs, and then you have 1 over I naught square. Okay, and the minus is due to the derivative. Now look at this term here, this V in 2L Fs d square, all this contribution here. Remember V naught square that we previously derived, V naught square here. V naught square is given by this expression, okay? V naught square is V in square, D square, 2L Fs. Okay, so what you can have here is exactly the same quantity that you can have here. So it's V naught square. And so we have V naught square over I naught square, which is minus there is an R. Okay, there is V naught here and I naught here. Okay, so this means that this is exactly minus V naught over I naught. This is V naught multiplied I naught over V naught. Okay, this quantity here is this expression here. And so this is minus R. Minus R. So the output, the small signal output resistance is negative R. So it's the same as the output resistance, okay, the load, but there is a negative sign. What does this mean? That you really have a negative output resistance? Or if you remember, this is typically this always happens when you compute the output resistance in DCM, also for buck, for boost, etc. I gave you the result for the small signal output resistance in previous case, if I remember. Then this sign happens to come out. What is the reason to have this sign here? Just a conventional, say, sign, because what does it mean computing the output resistance of a system? Okay, suppose that in this box you have a circuit to which you want to know the output resistance. For example, looking at these two terminals here, the operation that you can, say, have for, say, computing this output resistance, you switched off all the independent sources that you can have in the circuit, apply a specific voltage or current test, for example, a voltage, okay, test source, VT, then you have a current with this specific direction, so entering the port, which is called IT, and that R naught is VT over IT. Okay, this is definition, so the Thevenin definition to derive the equivalent resistance between any two pair of terminals in a linear circuit. Okay, but in that specific situation, which is the buck boost, but this happens in all the discontinuous conduction mode topology, you have the output port, which is this one. And the current, which I defined at the beginning, I naught, is this one, okay? And so for me, R is defined as V naught over I naught, okay? This is definition of the resistance R in my circuits. So I naught, if you look, I naught has a direction which is exactly the opposite of the direction of IT in the standard definition. So this is the reason why you get the negative sign here, because it's computed by a different convention about the sign of the output current, okay? This don't mean that you have negative resistance. You have the resistance R, okay? The negative sign is due to this sign convention, okay? Another parameter that is important is the gain. The gain is defined as variation of the output voltage, variation of the duty cycle. And so that means in our case, the derivation of minus V in, then you have duty cycle R to L Fs. So this is simply negative V in R to L Fs. Okay, so as you can see, it depends on the input voltage, for example. So if the input voltage increases, okay, the gain, the absolute value of the gain also increases, but also depends on the R, depends on the frequency, etc., etc. So this is what happens for the DCM. So let me just spend a few words about the waveform of the current through this DCM buck boost. I try to interrupt the sharing. Okay. So let me discuss a very short way, because now I think that you have the feeling how to, let's say, compute all these parameters. And so this is just a review of what we already did for other topologies. So nothing surprising here. We are in the DCM, okay, discontinuous conduction mode, but we can get the same reasoning already done. Okay, for example, for the switch, the current is simply the switch through the inductor, okay, when the switch is on. So if this is the current through the inductor, IL, okay, the current through the switch is simply IL during T1, okay, and null in the situation in which the switch is open. So T2 and T3, the switch is, there is no current for this. So you have this, say, triangular current. You have to compute the root mean square value, and you have also to compute the average value, okay? About the average value, what we can say, but the average value of the current flowing to the switch is the same as the input current, okay? Because no DC current can flow through the input capacitor, always the same reasoning. So the average value is I here. How can you get the average value of the switch? But the input current is always given by this expression here. I employed several times during these lectures. So since the power at the input is the same of the power at the output, okay? So V in multiplied I in is equal to V naught multiply I naught, then follows that I in is the conversion ratio multiplied I naught. Okay, so the same conversion ratio you can have for the voltages, then you can also have for the current, but in the opposite way. Okay, and so this means that I naught is V naught over R, and then you have MDCM. Okay, MDCM is not reported here. This was computed before. Is negative V in is negative D multiply the square root of R divided QLFS, and then you can put here, and then you can have the average current, which is the maximum voltage that you can have when the switch is open, the same as in CCM. So V in minus V naught. Totally positive voltage because V naught is negative. So this means that these transistors should withstand a very large voltage when it is open, so very large breakdown voltage to be chosen. Root mean square value. Root mean square value, you can compute this root mean square value by applying the definition. So square this waveform. When you square this waveform, you can have something like this. Okay. Okay, not well drawn, but it is a parabolic triangle. The peak value of this parabolic triangle is Imx squared. Okay, and you have to compute the area, and then you can average this area over Ts. This area is the area of a parabolic triangle, is 1/3 of the area of the rectangle that includes this parabolic. See? And the rectangle has area which is T1 multiplied Imx square, T1 multiplied Imx square, divided Ts. Okay, so if you have 1/3 of T1 multiply Imx square divided Ts, you can have the root mean square value square. Okay, and so you can have at the end T1 over Ts is the duty cycle, so you have this expression here. Okay, already derived a few times in the past. Okay, Imx is already defined before. Given the slope V in over R and T1, you can have Imx already computed. And so you can have some simple algebraic steps in order to derive Imx and I switch root mean square value. Okay. Finally, you should have this expression here, okay, which is the maximum current. And so if you get this maximum current you replace here, you can have this expression for the root mean square value. Okay. Diode current. Again, the diode current is the same as the inductor current when the switch is off, so during T2. And so you get, again, a triangular waveform. Okay, so what is important here to know? The average current value, because it's the average current value that induces the conduction loss, by which we can compute, we can estimate better the conduction losses. Okay, so which is the average value? The average value is the same of the output current I naught. Okay, basically is negative I naught because the direction of ID and I naught is, let's say, opposite one to the other. Okay, so we have negative I naught. This is the reason why in this expression here I put the absolute values of I naught. Okay, V naught over R, average value. This is the same of what we computed in CCM, of course. The peak value is the same. The maximum value of the I naught current depends on the minimum resistance that you can have. So typically, when you have to design components, you have to consider the worst case situation. Okay, so for the conduction losses, this means that you have to compute the maximum average current flowing to the component. So you have to consider the minimum resistance that you can have by specifications. Reverse voltage maximum is the summation of the input and output voltage as in CCM, so already done. And so we can also compute the root mean square value, because the root mean square value of the current flowing through the diode is useful to compute the root mean square value of the C0 capacitor current. Okay, so the same procedure as before. Now we have triangular waveform. You can square it, then you can have the average value of the this waveform across Ts. Okay, so nothing changed with respect to before. So we have to square this waveform. You can get something which is, say, something like this. Parabolic triangle. Im(x) square as a peak value, T2 as a base. So 1/3 of T2 Imax square over Ts. And then you can have your root mean square value, okay? Exactly what is written here. Imax is already computed. D2 is given by this expression here because it's simply derived by these these slopes here. Okay, this is T1 and this is T2. Okay, this time interval. We have the slope of the current during T1. We have the slope over T2. This is V0 over L, and this is V in over L. These two, say, quantity are the same, so this vertical variation of the current is the same during T1 and during T2. So we can say that, for example, V in over L multiplied T1 is the same of V0 over L multiplied T2. By using this expression, you can derive T2 over Ts. And so you can find this expression here. And you can put this expression in this quantity here, and then you can derive all your expression. Okay. At the end of this block of slide, there are all the equations that you derived, and they are complete. Okay. Input current, you have to apply the quadratic Kirchhoff current law, okay, because the current is simply the difference between the root mean square value of the switch current minus the square value of the input current, okay? So this expression here was already derived before. Here, the average value is something that we compute here, so we can get the differences, okay? What happens for the output capacitor? The same. Quadratic Kirchhoff current law here, in which the root mean square value of the diode was specifically computed before for that reason here. I0 is V0 over R, so you easily compute it. Okay, you can derive this expression. As you can see, the steps for deriving and the basic knowledge is very limited in this kind of representation because the wafer more or less have always the same behavior, okay? So you can use flap top approximation, or maybe when you have triangular wafer, you can use the definition. You have to be very, focus your attention on the nodes in which this currents happens, but there is no difficulties in, deriving this expression. I hope so. If you have some problems, you can say something to me, you can contact me, etc. Okay, buck boost, CCM and DCM, classical analysis, which is in steady state. I just mentioned at the beginning of this discussion yesterday some of the benefit of having a switch in series with the power flow, okay? This is exactly what happens in the buck, for example. And this is not surprising that you have here the same, advantages that you can have in the buck, because the input side of the buck boost is exactly that of the buck. So you have a switch in series with the current flow, series with the power flow. So this means that I'm able to manage short circuits at the output. Okay, when the control, which always is combined with the converters, recognize the presence of the output short, because the output voltage, the measured output voltage, collapses to zero instantaneously, the switch is immediately left open in order to avoid that the short at the output induces malfunction in the input source. Okay, so the load adapter can be managed very, very well. In-range current, the same. At the turn on of your buck-boost converter, a large amount of charges are provided by the input source to charge this capacitor, which is discharged 0 voltage across it, in order to increase its voltage to, say, the standard output voltage. Okay, so that means that you can have, for a very short time interval at the beginning, at the turn on of your buck boost, a very huge current. This huge current flow through components, inducing sometimes malfunction due to the presence of parasitics, can induce, let's say, electromagnetic compatibility issues, etc. So it's important to reduce this stress. Even the stress happens just one time when you turn on your converter. It can be very large, can upset the operation of your converter. What can you do to manage this kind of problem? You can increase the duty cycle slowly from 0 to the, say, steady state value of the duty cycle, okay, in order to have, let's say, a flow of charges which is not instantaneously, but, let's say, is done in a certain time of period. So you can, say, enlarge the time base to which the same quantity of charges are provided to the load. So this reduces the current that you can have. Okay, this happens the same in the back. So the switch in that position is very useful. Drawback, the switch in that position has the drain, which is connected to the input source. So if the input source here has some over voltages due to whatever in your applications, in your operational environment, then also the drain of this MOSFET can, say, goes up and down. And so that means that typically these can, when the MOSFET, for example, is off, the voltage VDS can be very large, exceeding the breakdown voltage of the MOSFET. So something that can be controlled, trying to reduce this over voltage at the input by filtering, etc. We know that for each of the basic topology I discussed with you, the buck and the boost, and so even for the buck boost, you can have the diode topologies, but also the synchronous topology, in which both the MOSFET and the diode are replaced by transistors. So they are made by transistors. Okay? So you have two transistors. So the same happens for the buck boost. We replace the diode, which is in this position, by another N-channel power MOSFET, SW2. Of course, in order to, let's say, to be coherent with the operation of the standard MOSFET and diode buck boost, we have to operate the two switches in a complementary way. When switch 1 is closed, switch 1 should be open, and the opposite is also true. That means that my driver should have a connection between the driver and the switch 1, but also connection to switch 2 by means of a logical NOT gate, okay, which, let's say, invert the control signal in order to make possible the, say, complementary action. So when the unitary switching function, the logical signal provided by the driver, is null, it means that you have 0 here, but you can have 1 here. So switch 1 is off, switch 2 is on. When it is 1, okay, when QA is 1, it means that you have 1 here, but you should have 0 here. So switch 1 open, closed, and switch 2 open. Okay, so this is exactly the same operation that you can have in a standard diode MOSFET buck boost. Okay, what is the drawback specifically in buck boost converter? That both these two switches are of I-side type. Means that no, the drain or the source of both the switches are permanently connected to the reference. Okay, the reference is here, and this is not connected in a permanent way to one of the two terminals of the MOSFET. So this means that this is an I-side switch. The I-side switch should be driven by specific gate driver, I-side driver that are expensive. They need specific components to be added, like capacitors or diodes. Okay, so is not the same having a low side switch, for example. Okay. These slides and a few of the successive slides try to answer to the question why this converter is called buck boost. Just to consider a few things. At the beginning, this converter was fabricated, studied, evaluated, and nobody's understood in that early times that this converter is the combination of the buck boost. This converter also have another name. Okay. Then, after the theory about converters establishes, so many people works on the theory behind this converter. They recognize that this converter is no more than a buck followed by a boost. Okay, so after the break, I'll talk about this kind of connection. Okay, it's important to understand how it can be derived a buck boost connecting the buck followed by a boost, because people that understood this kind of mechanism also asked why we cannot have the boost followed by a buck. So it is possible to have the boost buck. Okay, so we can answer this question later. Okay, 10 minutes break, so 10 and 2 minutes we can continue. Thank you very much. Okay, let's continue this discussion about the derivation of a buck boost by direct connection of a buck and a boost. Buck connected to the input and the boost connected to the output. Okay, in order to do that, let me share my widescreen. Okay. Okay. So buck boost as connection of buck and boost. So let me draw a buck with all these capacitances, C naught, okay, then you have V in here. This is the switch 1, okay, and then the boost. C naught, V naught, switch 2, L2, diode, etc. Okay, so we have the buck and the boost. So take these two converter topologies and let's say combine in cascade, okay, connecting the buck to the input side, to the input source, and the boost to the output load, okay, in that way. So if you made this combination, the circuit becomes this one. So you have to L1, L2, then you have C in, you have the diode, and C naught. Okay, I put exactly the two circuits in cascade. Okay, so I connected in this way. So we have V in is here, V naught is here. Okay, so now we should remember something that I said at the beginning of the discussion, for example, in the boost and the buck. I said that, for example, in the buck converter, the output capacitance, which is C naught, this one, is not strictly essential to the operation of the buck. Remember, I need a low-pass filter, okay? But the inductance L1 with the resistance connected to the load, connected at the load side, is itself a low-pass resistance, okay? So basically the buck can work, can operate as intended, even without the C0 capacitance, okay? Of course, I always insert C0 capacitance in order to increase the filter order from first order to the second order, so you have a LC low pass filter. So this is always done. But basically, the buck can operate without this capacitor. So if I remove these C0 capacitances, we have again the buck converter. Okay. What happens for the input capacitance for all the converters? The input capacitance, strictly speaking, again, is not essential to the operation of any converter. Okay, any converter I described to you up to now can operate in the way I explained without the presence of C in. Many books, many textbooks describe the operation of the buck, the boost, buck boost, etc., without insertion of C in, because the input voltage V in is constant. Okay, so since I have this assumption, okay, and this is one of my basic assumptions, V in is constant, the insertion of a bipole, which is in parallel to a constant voltage source, has no meaning. Okay, but I have to think that in practical circuits, no source is constant. It has some, they have some output resistance, etc. And then always you have to insert a low-pass filter at the beginning, at the input side, because you have to, contain the electromagnetic emission inside the converter, not, to expand all over surrounding equipment, etc., etc. So basically, you can say that even the C in capacitance can be eliminated, okay? The operation of the converter is always the same. So there is no modification of standard operating mode of the converter if I eliminate C0 for the buck and C in for any converter. But if I eliminate these two capacitors here, okay, now I have L1 and L2 that are in series, okay? So in place of L1 and L2, I can put just one single inductance. L1 plus L2, okay? And this is what happens in this converter. So I found out another converter. And this converter, what kind of relationship between the input and so, which is the conversion ratio. But V in, and we can say V in prime is, this is a boost, which is 1 minus D. This is V naught over V in prime. V in prime is the same in this connection of the output voltage of the buck, but we know that in the buck, V in prime over V in is D. So combining these two, we can say that V naught over V in is V naught over V in prime multiplied V in prime over V in, and so this is D over 1 minus d. Okay, this is the conversion ratio of this new converter. As you can see, this conversion ratio is the same of the buck boost. The difference is that now this is positive, okay? It's not negative, okay? The buck boost is d over t minus 1. So this, if you want, this combination, these circuits, is the non-inverting version of the buck boost. The buck boost inverts the output with respect to the input. This is has the same relationship, the same conversion ratio of the buck boost without inverting the output voltage. So V0 is positive, okay? Let me redraw these circuits by employing a, let's say, synchronous version of this one. So let me redraw this non-inverting buck boost. Non-inverting buck boost, replacing the diode with two switches, okay, in the classical derivation of synchronous converter. So I have this switch here. So I have the inductance. I have another switch here. And so I have these two switches. This is L. Let me call this L series, okay, because it's the series L1 plus L2. C in, V in, C naught, this is V naught. According to what I written in the slide, these are S1, S switch 1. This is not S switch 2, but is switch 4. Okay. So this is switch 4. This is switch number 2, and this is switch number 3. Okay. So I replace the diode with, say, active switches in order to have the synchronous version. Okay. Let me discuss in which way I have to command this switch. Okay. Switch 1 and switch this diode D in the back acts in a complementary way. Okay, so when the switch 1 is closed, the diode D is open. So that means that if I want to drive with a unitary switching function Q, I have to drive switch 1, but I have to put a logical NOT signal to drive the switch number 3. Okay, in order to have, when Q is 1, switch 1 closed, switch 3 open. When it's 0, switch 1 open and switch 3 closed. For the boost, the main switch now is this one. This is the MOSFET. So this MOSFET here is closed in the same time interval in which switch 1 is closed. Okay, while the diode is closed in conjunction in the same time interval in which also the diode D of the buck is closed. So, in other way, I have to have for switch 4, sorry, the same unitary switching function of the switch 1. While for the diode, switch 2, I have to have the same logical inversion of Q that I have for the diode, the switch 3. Okay, so I have to command simultaneously switch 1 and switch 4, okay, and simultaneously switch 2 and switch 3. So in the same way, I have the combination that leads to the non-inverting buck boost. Okay, so when Q is, let's say, 0, when the Q is 0 means that switch 3 and switch 2 are on. When it is 1, switch 1 and switch 4 are on. Okay? So, what happens when you are in the situation in which Q is equal to 1? Okay, when Q is equal to 1, this logical signal forces the closing of switch 1 and switch 4, you are in the time interval that we call T on. Okay, while when is 0, so when the switch 1 and 4 are open, this is T off. Okay. So what happens during T on? Switch 1 and switch 4 are closed, so they are on. And so that means that, let me redraw the circuits with switch 1 on. Diode is closed. So you have, diode is open, sorry, L series. And then you have here the switch 4. The circuit is this one. C naught, and then you have the output resistance R. Okay, so what happens in this phase? That we recognize what I previously called the charging phase, in which the input source charges the inductor L. In order to have this current, the current flowing to the inductor reaches the peak value, the Imax value. Okay. What happens during T off? During T off, we have that switch 2 and switch 3 are on, while switch 1 and switch 4 are off. So in that situation, we have, let me redraw the circuits with the switch 1. Switch 2 on. This is an inductance. And switch 3 on. R with V naught. Okay, so the other two switches that are connected here are off and off. So in that phase, we can recognize the phase in which the inductance L series, in this case, discharges. Discharges through the load this way. So again, we have two different situations. The first one is that the charging phase. Followed by the discharging phase. So again, we have that in all the two situations, in both the situations, we have no direct connection between the input and the output. As you can see here, there is no connection in the charging phase, but again, there is no connection between the V in and V naught in the discharging phase. So these circuits has a conversion ratio which is the same of that of the buck boost, but non-inverting. And as the buck boost is an indirect converter. Remember that we define direct converter like the buck or the boost converter in which there is a phase in their operation, in which there is a direct connection between the input side and the output side, or an indirect converter like the buck boost, in which this not happen for any time interval. Okay, so this is the same properties of the classical standard buck boost. Another thing that we can learn looking at these circuits is the following one. Look at the inductance L series during the charging phase. During the charging phase, the inductance has this terminal here, the right terminal of this inductance, which is connected to the reference. Okay? Look at the discharging phase. The same inductor now has the left terminal, which is connected to the reference. So, one of the two terminals of the series inductance is always connected to the reference terminal in charging or discharging phase. Okay, so we can think of this condition by having a topology change in order to have always the same terminals of the L series inductance connected to the reference. Okay, we learn that the inductance has one of the two terminals, not the same, right or left terminals, which is connected to the reference. I made some topology changes in this circuit in order to have the same terminal of the inductor always permanently connected to the reference. So that means that I have to put not the inductance, let's say, floating like in the previous circuits, but with one of the two terminals permanently connected to the reference. Okay? If I made these topology changes, okay, I can have the same behavior as before if I have just two switches like this. Let's say switch 1 and switch 2. V naught and V in are always here. Okay. These two switches are operated in a complementary way. So when the switch 1 is closed, the other one is open, and the opposite is also true. Let me analyze this circuit, which is a direct derivation of the previous one. Okay. During, for example, the phase which I call the charging phase, the on, in which switch 1 is on and switch 2 is off. When the switch 1 is on, so that means that I can replace the switch by a short circuit. Now the inductance is connected in this way, so it is charged by the voltage V. This is exactly what happens in the charging phase of these circuits. Exactly the same. Okay? As you can see, the circuit is the same. When you have the discharging phase, it means that you have to open switch 1 and close switch 2. In that situation, this is open, this now it's closed, and there is, let's say, the discharge of the inductors on the output side. Again, there is no direct connection in any of the two phases between the input and the side, so we have an indirect converter. This discharging phase exactly acts in the same way we did for the previous derived buck plus boost connection. The only difference is that in that circuits that I analyze here, the inductor's terminal, which is connected to the reference, changes. okay? Now is the right terminal and this is the left terminal, okay? While in this configuration, I recognize that one of the two terminals is always connected to ground, so I made some topological changes to fix it. The terminals connected to ground now is always this one. And so, since there is no variation of this terminal, the output voltage is reversed. So, what happens here is that my relationship, again, between the output and the input, so the conversion ratio is VO Vin. But this circuit here is the buck boost. As you can see here, these circuits that I designed here, this is the classical inverting buck boost that I, let's say, explain to you. Okay, this is the MOSFET, and switch dual should be the diode, for example. Okay. So as you can see, I derived the buck boost simply by reasoning about the connection of a buck on the input side and the boost on the output side. Recognize that it has the same properties, okay, and deriving what is called the non-inverting buck boost, having the same conversion ratio of the buck boost, but not inverting the output side. I made a topological change to make fixed the terminal of the inductor, which is always connected to the reference. I lose the possibility to have the output voltage positive. Okay, now the voltage should be what is changed, what is reversed, is not the terminal of the inductance, is the output voltage, which is now negative. But anyway, I derived this, say, buck boost exactly as a combination of buck of the boost. In power electronics, typically you can find situations in which, before understanding the theory and several, let's say, features that a circuit can have by studying, let's say, derivation, topologies, etc., they are used. Then are used without too much theory. And then someone start to understand if this is the way to understand the circuits in a, say, more classical way, to study the equation, etc. This in power electronics happens very frequently in the past. A typical other situation in which, before understanding the theory, it was largely employed is the control block, the controller of the power converter. Typically, they were controlled without understanding fully the theory. Okay, someone put, say, some specific circuits, not understanding why it has to do that, but then the theory established well. Okay, there are a lot of paper discussing, let's say, the equation, etc. And then all that situation that previously was done, say, by, say, some guru in the firm of power supplies, then are formalized in a very standard way by equations, and though they can be studied in a different way. Okay, so this typically comes out in electronics, but specifically in power supply it happens. And this is also for the buck boost. So when it comes out that you can derive a converter by simply put some specific basic topologies in cascade, for example, the buck and the boost give us the buck boost, someone tried to ask himself if there is the possibility, for example, to put a boost followed by a buck in order to get what is called this in this sense the boost buck. Okay, so let me discuss the boost buck if you want. So let's cascade a boost plus buck. So I have to draw boost on the input side. This is the switch. Then you have C0. And then you have C in, L or L1, switch 1, diode 1, C0. This is V in, this is V0. This is the boost. plus at the output side we can connect the buck. L2, switch to C in, C not, the same topology that we know. This is V naught. Okay, and this is the buck. Okay, so connect in cascade, so that means that I have to connect in this way circuits. C not, C in, switch 1, switch 2, 2. Then you have V in, and then you have V naught. The voltage here is Vx. Okay, so what we can say? The same, say, discussion we had before. The input capacitor of a converter is not strictly essential to the operation of that converter. So we can skip C in, for example, but we cannot skip C naught. Okay, so if you want, this capacitance here includes the, say, the parallel of the two, if you want to take two, but anyway, C naught is essential to the operation of the boost. So let me consider that here you have just one capacitance, okay? V naught over V, this is Vx, or V prime as I called before. V naught over Vx for the buck is the duty cycle. Vx over V in for the boost is D over, let's say, 1 minus D. So the multiplication of the two, which is V naught over V in, is again, sorry, this is the boost. 1 over 1 minus D is D over 1 minus D. This is the conversion ratio of this converter. So it's the same conversion ratio that we had for the non-inverting buck boost as I previously done. So we can call, if you want, also in this way. It is another version of the previous one. As we did before, try to, say, modify the circuits by taking the synchronous version. So replace the diode by other switches. So this is the diode that now is a switch 3, this is switch 1. I put here just a single capacitor at the node X. I have here the switch number 2. Then I have here another switch, which is the diode, switch 4. Then I have L2, C naught, V naught, C in, V in. Okay? Synchronous version of the same circuits. Okay? I replace the diode that are here with two switches, switch 4 and switch 3. Okay. Again, I have to command the circuits in a specific way. So, for example, I have to say that when switch 1 is closed, then I have to close also switch 2. Okay, so these two switches should be closed and opened simultaneously. The diode, the same. The diode should be closed and open simultaneously. So the circuit that comes out is a circuit that has a driver. Okay, this driver has a function which is, say, commanding switch 1 and switch 2 with the same unitary switching function, Q, Q, and Q, and command switch 3 and switch 4 by inverting Q. So we have Q naught, and you have, let me draw in this way, Q naught here. Okay, so when Q is equal to 0, they are on switch 3 and switch 4. When Q is 1, are on switch 1 and switch 2. Okay, so again, let me analyze what happens when I am during T on during T off. During T on, switch 1 and switch 2 are on, so the circuit becomes this is C. Let me call this C. C, then I have switch 2 which is on. Okay. Be in. Okay. These are the position of the switch that are open here. Sorry, not exactly there, but here. Here. Switch 3 off and switch 4 which is off. Okay, so in that phase we can recognize the charging phase of the inductor. Okay, while the output side, the output voltage V naught, is held to a constant value by the charge in this capacitor C naught and this capacitance. Okay, but there is no direct connection between the input and the output. What happens during T off? But now during T off, switch 3 and switch 4 are on, and so that means that if you want to redraw the circuits, is circuits like this. L1, the switch is open, switch is open, L2, C naught, and then you have the connection here. Switch 4 on, switch 2 off, switch 3 on, and switch 1 off. V in, C in. Okay. Now what happens? In that specific situation, we have that as you can see here, the capacitor is connected to the input side. Okay, while in the on situation was the, let me change the color, was C connected to the output. Now the capacitor C is connected to the input. Okay, so instead of looking what happens to the inductor, okay, we can and so we can distinguish, for example, a say charging phase here of the inductor, but we can recognize here a discharging phase of the inductor. Okay, so it means that we have to focus our attention not just on the inductance. By the way, we have two inductors, so which of the one we have to consider? It's not easy to say. Look at what happens to the capacitor. Okay, so the T-on phase, during T-on phase, the charge accumulated in the capacitor C is shared with the output side. Okay, is say provided to the output side. So if you want to call T-on as the term discharge or charge and referring to the capacitance, you have to call this phase as a discharging phase, because it discharges the capacitance C. If you now look at the capacitance C, even T off has a meaning, because T off C is connected to the input side, so we are in a phase in which the capacitance C is charged. As you can see, in that case, is most useful to look not at what happens to the inductance, but look what happens to the capacitance. Okay, so in this case, we have a dual consideration with respect to the previous circuits. Okay, we replace our consideration that we made about the inductance, series inductance L1 plus L2 before, with the consideration that we can have to the capacitance, and we can have this dual, say, substitution, a C in place of L. We have the same reasoning. We have a charge phase of the capacitance during T off now, discharging phase of the capacitance during T on. Okay, so this circuit is dual in this sense that we have to replace T on with T off, and the capacitance C, the inductance L with the capacitance C. In that way, we have T off with the discharging phase of the capacitor, T off with the discharging phase through the load of the capacitor. What can we also consider? Okay, so this is as a converter that has the same conversion ratio, T over 1 minus D, of let's say the non-inverting buck boost. Okay, so V naught is always the same sign of V in. Is an indirect converter. Okay, because there is no direct connection between the input side and the output side, as in the buck boost. One terminal of the capacitance here is always connected to the reference. But we can have a topological modification of the circuits, which is exactly the opposite topological change that we made for the buck boost. Okay, previously we recognized by the analysis of the buck plus boost converter that the inductor has one of the two terminals, but not always the same, connected to ground. Then we made a topological change to fix it permanently one of the two terminals to the reference terminals node. Here the opposite happens, because this is a dual circuit. In this case, we have just one terminal permanently connected to the reference, but we want to make a topological change that make, say, not the same terminal connected to ground. In order to do that, we can modify these circuits by putting the capacitors floating this way. And if you make this capacitance floating this way and you put two switches, like, for example, this one, switch 1 and switch 4, and then you have the two inductance L1, L2, and they're always present, C in and C not. We have V naught, V in. So we made a topological change in which now the capacitor C has no fixed terminal connected to the reference. What happens during the time interval that I can call T on? Let's start by T off, okay, which is it's a better description. T off means that switch 1 is off and switch 4 is on. Okay. In that situation, this switch is closed. Sorry. This switch is closed. This other one is open. What happens in that specific situation? That we have charging these capacitors. Okay. So you are charging this capacitor, and this terminal, the right terminal of this capacitor, is connected to ground. We have the charging phase. During T on, which one is on, which 4 is off. So in that case, it happens that this one is closed, this is open. Now is the left terminal, which is connected to ground, okay? And it is the output side that received the charge from the output from the C capacitance. Okay, so we have the discharging phase. Now the polarity of the voltage across this capacitance, okay, one during the charging phase, this voltage, this capacitor is charged with this polarity. Okay, the plus is here and the minus is here. Okay, then when you pass from the charging phase to the discharging phase, the plus goes here and the minus is here. So the plus is here, the minus is here. So that means that the output voltage change its polarity. Okay, so the same discussion that we had previously means that now V naught over V in is D over, if you want, D minus 1. Okay, so this means that it is negative. So this kind of circuits are the same conversion ratio. We are talking about CCM, okay, not complicating too much the discussion. The same conversion ratio of the buck boost, okay, inverting one, but it has a different topology. Okay, this circuit is not called boost buck, like say someone can say proposed, but is called by the name of its inventor, which is Professor Chuk. Okay, I don't know the correct orthography of this name. You can find different spelling, okay, but the pronunciation is Chuk. Okay, so Professor Chuk derived these circuits exactly in this way. Okay, and he found out a circuit which is totally dual. The topology of the circuit is totally dual of that of the buck boost. Okay, the charging phase and discharging phase are made by the capacitor, not by the inductance. Okay, the capacitor now is floating while the buck boost is connected to ground at the same conversion ratio, which are other properties. Look at what happened, for example, the node, remember, input node and output node. If you look at the input node and the output node, you see that there is an inductance which is in series. What does it mean? That the current flowing to this inductance has always a smooth behavior. So that means that if you look at the input and output capacitors, that these input and output capacitors are not so electrical stressed as much as they have as they can in the buck boost classical topology, in which in place of two inductances you have two switches, a MOSFET and a diode. So these kind of circuits make possible to have, let's say, smooth quantities, less root mean square value of the current flowing to the input and output capacitors. Okay. Other properties, which is the maximum voltage across switch 1. The maximum voltage across switch 1 is the voltage that you can have when the switch is open. When the switch is open, it means that you have in the T-off phase. And during the T-off phase, which switch 4 is closed and switch 1 is open, the maximum voltage is V in. So switch 1, maximum voltage is V in. So it's an advantage, because remember what happens in the buck boost. In the buck boost, the switches as V in minus V naught, which is negative. So very huge voltage. Now the switch V in is not so huge like the MOSFET you have to use in the standard buck boost. Okay, the breakdown voltage is, let's say, less. In the breakdown voltage is reduced. It means that also the R-on resistance is reduced. There is a strict relationship between the R-on resistance that you can have in the closed MOSFET and the breakdown voltages. Okay, MOSFET with larger breakdown voltages always have larger R-on resistance, which induces higher, say, conduction losses, etc., etc. So this can be a benefit. For the switch number 4, which is the maximum voltage you can have in the switch number 4. But with switch number 4, when it is open, is exactly the situation depicted in this figure. So it means that switch 1 is on during T on, switch 4 is off, and the maximum voltage is V naught. Okay, is the voltage across the switch. So which is the working, so this is a benefit again, which is the working voltage across this capacitor. This capacitor has a working voltage which is V in minus V naught. V naught is negative, so it is a quite large voltage. This is a, say, difference with respect to the buck boost, because we have here a topology in which you have a capacitor with working voltage is very huge, is very large. Okay, so this sometimes for applications in which this voltage is large, you can have problems in find reliable capacitors with working voltage that is so huge. Okay, you have also to think about that in that topologies you have two inductances, okay? And while in the buck boost, which is this one, you have just one inductance, okay? Inductance can be expensive sometimes, depending on the specifications, but it's always better to have a circuit in which you have just one inductance and not two inductors. Don't you have a large number of inductances, okay? Then you have just two capacitors, and then in the Chook converter you have three capacitances, okay? Here in the buck boost you have two high side switches, and in the Chook converter, the switches are low side switches. So this is also another benefit. Low side switches. Again, we have to say that we have some difficulties, like the buck boost, to make this circuit stable operating in CCM. Okay, so the same drawback. In which way you can control, for example, a short at the output? If you put a short circuit at the output and you want to interrupt what's happening, the best thing that you can do is to left open both the switch. If you left open both the switch, practically there is no galvanic connection between the input side and the output side because there is a capacitance here that separates the two. So it can control the output circuits, the output short circuits. Okay, by left opening switch 1 and switch 4, let's say there is the galvanic separation of the input circuits to the output circuit because you have the voltage, that you have this capacitance. Okay. So this is the fourth topology that we can have. I have a question, so let me answer these questions. Okay, Mattia Miscali, can you repeat how V0 over Vin is calculated? V0 over Vin in the Chuk converter, okay, is computed in this way. Simply the product of the conversion ratio of the two converters that you are connected in series. For example, if you have as in this slide is shown, the Chuk converter, so you have the buck and the boost, I can say that the conversion ratio of the buck is V0 over this voltage here, and this is D. Okay, this voltage versus this one, the output versus the input. For the boost, this is 1 over 1 minus D, CCM boost, the output versus the input. When you put this block in a cascade, then you have to multiply these two conversion ratio, okay? V0 over Vx multiplied Vx over Vin. And so you can get D over 1 minus D. Okay, you have two blocks that are specific, let's say, relationship between the input and the side. When you put in cascade, so in series in this way, you can have the multiplication of the two conversion ratio. This is for the Chuk, but this all is the same for the buck boost. Okay, they are reversed. You have the boost and the output and the buck at the input, but then you have the same conversion ratio, so you get the same product. I hope that this clarifies, Miscali. D divided D minus 1. Let me check. Maybe it's possible. This is correct. Okay. Let me share the screen to see. No, here is let's say this one and D, and so I get D. This is correct. Pay attention that this is correct, and so I said the same in the whiteboard. But then when you make the topological changes, and in this case for the Chuk converter, I made this capacitance C to be floating, not connected permanently to, say, the reference, but be floating, like in this way, then the output voltage becomes negative. And so I have to change the conversion ratio from D over 1 minus D to D over D minus 1. Because in this situation, when you charge the capacitance, you charge the capacitance with a voltage which has the plus sign and the minus signs with this polarity. When you discharge this capacitance, the plus and the minus sides are connected to the load in this way, because this node is fixed. Okay? When you change the topology in this way, look at what happens when switch 4 is closed. When switch 4 is closed, you are charging the capacitor with plus or minus in this way, because it is in parallel to Vin. But when you open switch 4 and close switch 1, now the plus sign is connected to ground, and the minus sign is the node which is connected to ground, to the load. So the voltage is reversing. In order to take into account for this reversing of the voltage, I have to, let's say, put a minus here. And I can put a minus here, or I can write down d over d minus 1, which is the same. Okay, the same happens for the inductor in the buck boost. Okay. Another question is Desario Federico. Why buck boost and shock converter are difficult to operate in CCM? It's always the same answer that I already done previously. They are derived from the boost, the buck boost, and the chuck, or the chuck, or the boost buck, if you want. So they include a boost. The basic drawback of a boost converter, and this is something that now I anticipate, but I say demonstrate in next week, that when you operate a boost in CCM, the loop gain of the closed loop that is needed to feedback your system, to close the system in a closed loop, to effectively control the system, then it has some problems in stabilizing it, because you have a zero in the right half plane on the imaginary plane. And this means that you have some problems. Okay, so take into account my discussion here. The boost CCM cannot easily control. Sometimes you can do that, okay, but in very specific situation. But generally, we can say that the boost CCM is very difficult to control due to the fact that the closed loop transfer function, the loop gain, has a zero in the right half plane. That means that you have a very poor phase margin, and it is not possible to stabilize for all the, say, conditions you may have in your circuits. This happens for the boost. Any circuits that are based on boost topology, the buck boost, the choke, which is the boost buck, inherited the same, say, bad feature that in CCM they are difficult to control. As I said before, take this sentence as, I say, matter of fact. We will discuss and demonstrate it. Okay. I hope that this clarify a little bit better what I said. Professor Maddaleno, former professor of this course, call all the circuits that are derived from the boost, like the buck boost or the chuck, are son of a boost. Instead, meaning that in effect they inherited this bad feature, okay, which is exactly the almost impossibility or very difficult to control them in continuous conduction mode. So you have to operate them in DCM. Okay. We can clarify this sentence later in this course. I hope that this a little bit clarify. So final consideration about the chuck converter, 2 inductors and 3 capacitors. So it is expensive, okay, but the input and the output current are smooth, so they can avoid disturbances exported in the input source or to the load. And finally, that capacitor has very huge electrical stress, means that the working voltage is very large, V in minus V naught, and V naught is negative. Okay, questions, other questions about this? If you have no questions, I want to start discussing some concept about the rectifications. What does it mean? Circuits that are connected to an AC source, like the, say, mains electricity, say, distribution networks that you can have at home, and provide at their outputs a rectified voltage, okay, a more or less constant voltage. Okay, they are rectifier circuits. Remember that when we classified power processing unit, the converters, we said that there are DC-DC, so power supply, that are discussing now, but also you have AC to DC, and this is called the rectifiers. Some concept about rectifier are strictly related to power converter that I discussed with you in the previous lecture. So let's start a very short discussion that lasts today and Friday about these AC to DC converters, not DC-DC, but rectifiers, in order to include also something that we studied in these lectures, okay? Next week, we can start about the modeling of power converter in view of designing the controller, okay? So, consider a network, and the network in this slide is called N. This network has an input port, okay? These are two terminals, and across this terminal you have a voltage, which is called VT, and to this terminal flows a current, which is called IT, okay? Supposing that these variables are periodic, and the period is T, okay? This don't mean that they are sinusoidal. We can move from sinusoidal in a few steps. But just suppose that these variables are, say, periodic, like the waveform that you can see in this slide, okay? You can expand this periodic waveform by using Fourier series, okay? Fourier series is a classical way to decompose a periodic waveform into a set of infinite sine waves, each of them having a specific amplitude, and each of them having a specific frequency. In particular, the frequency of each component of a Fourier series is a multiply of a fundamental component, okay? For example, the voltage V can be expanded in Fourier series by taking into account an infinite series, infinite summation of sine waves that can be, say, expressed in this exponential way. Vn is V1, V2, etc., the amplitude of each of these components, and n multiplied omega is the pulsations of each of these waveforms, okay? As you can see, n is an integer, so it means that you can have a fundamental, which happens when n is equal to 1, and then you have the harmonic of this fundamental component that are integer multipliers of the fundamental. The same happens for the current, Im, etc., etc. So we can characterize this network N by looking at the instantaneous power. Okay, the instantaneous power is the product of the voltages Vt and the current It flowing at that terminal. The instantaneous power, changes time to time, instant. Okay, if you look at, for example, power electronics, the block N, which is the network we are assuming in this discussion, typically includes several reactive elements, okay? And the reactive elements store some energy. So that means that the instantaneous power is not the correct way to analyze circuits that has element that stores energy. Because sometimes it happens that, for example, if you look at the output power, it happens that the output power has no link to the power that is absorbed from the input side at that time instant. So the instantaneous power changes time to time is not so important in circuits in which you have reactive elements storing energy. It's much important. The value is much higher, not the instantaneous power, but the average power over the period of the electrical quantities, okay? So what we can do is to think about the average power, taking into account that we already discussed the average power in our converter, okay? When we say that P in is equal to P naught, I always made this assumption by taking into account the average power, not the instantaneous power. Okay, look, for example, what happened in the indirect converter. It happens that you are drawing during T1 power from the input side, but the output power is something that is stored in a previous cycle by the output capacitance. So it's better to understand what happens in a period, averaging the power in a period, not talking about instantaneous power. So the average power is defined by the integral. Here is 1 over the period, the integral extended to the period of the product of the voltage and current. Okay. If you put V and I defined in this way, in this integral, what happens? Let me discuss this point sharing my whiteboard. Okay. You have that V is a summation over n of Vn E j n omega t. The current is the summation over, now we can call M I m E j m omega t. So you can get the average power as 1 over t of okay, you have to multiply these two summations here. What happens when you get the multiplication of this sine wave? Okay, you are multiplying sine wave. At a certain point, you can have multiplication, for example, of Vn multiplied Ejn omega t multiplied Im Ejm omega t with m which is different from n. Okay, it happens that when you develop these two summation, most of the factors that you can integrate are of this form. Okay, m is different of n. It means that the frequency here is different from the frequency of the other. So you have two sine waves that have different frequency. Okay. And you have to integrate over over the integral from 0 to t. When you get this kind of integral, this kind of product gives over the period t a contribution which is null. So the only contribution that brings a not null power are the multiplication of components of the voltage and current that have the same frequency. So you have a power which is not null only when you multiply components that have n which is equal to m. Only for component of the Fourier expressions that have this kind of contribution. Okay, this is, sometimes this condition is indicated as orthogonality of the functions. Okay, when m is different to n, then you have that the two functions in the Hilbert spaces are orthogonal one to the others. When you get the integral, this come to 0. Okay, the integral over a period t. So the power is null only for the component that have the same frequency. This means that if one of the two variables, I don't know, the voltage, for example, is just a sinusoid, having a frequency, specific frequency, then the power, average power, is not null for the component of the current at that specific frequency. If the voltage V is constant, so that means that the frequency is null, is a DC, then it means that the average power is not null only for the DC component of the current I. Okay, this is very important to understand. Okay, you have, say, not null average power only if you consider the same frequency component in the two variables that you are multiplying, okay? Okay, we can continue Friday, because now the situation, if I start now, I have to say continue. But we can start from this basic concept, okay? When one of the two variables is just one single frequency component, DC or specific frequency, then the power is not null for the component of the covariable. Here is not covariable, it's covariable, okay? That has the same frequency, okay? From this point, we can start Friday morning at 10 a.m. to end this part, okay? Friday afternoon, there is the LED 5, so people that are interested can book their seat by the standard way, okay? If you have question, I can say answer your question. We have some minutes to discuss if you want.